Okay, so we're going to be solving the second problem in the vapor compression cycles and cascade cycles practice worksheet. So second problem is the Cascade R system. First, I'm just going to write down the cycle and the states. So you can see there are 8 states in the cycle. So it looks like 2 simple vapor compression cycles combined with a heat exchanger. And now we're going to be adding the known thermophysical property values that we have, which are the low, medium, and high pressure. Also, if we look for the TS graph, constant pressure we know is in the evaporator, so from state 4 to 1, constant pressure, and it's the low pressure. So we know P1 equals 140 kilopascals, state 4, P4, then the medium pressure is 320. Looking at our TS diagram, we know that 3, 8, and 5 is the medium pressure. Okay. And the high pressure is 800 kilopascals, and that's of the condenser. You can also see here from the TS diagram, constant pressure. Oh, I'm sorry, before we go to the high pressure, constant pressure also is at state 2 for the medium of 320 kilopascals. So for state 2, P2 equals P3. Now when we go back to the high pressure, state 6 and 7 of the condenser have a constant pressure of 800 kilopascals. And now we have one thermophysical property value for every state, and we only need 2 to solve the rest of the thermophysical property values for every state. So to find a second one, we can look at our TS diagram, and since it's an ideal Cascade R system, we know that at state 1, it's going to be a saturated vapor, so the quality is 1. So X1 equals 1. And right now, we're going to solve the rest with the built-in functions into E. So options, function info, thermophysical properties, ideal gases. This is, I'm going to assume mass flow rate. Alright, so the problem description doesn't give a working fluid, so I'm just going to do real fluid. Put in R134A. And then if you have to do a different working fluid, it's the same E steps. You would just input a different working fluid into your equations. So I'm going to choose real thermal props because it's a real fluid. If you're choosing an ideal fluid or an ideal gas, it would just be called ideal thermoprops. So we know pressure, and our second independent property is quality. Paste. We have our working fluid, and again, you can just change this value if you have a different working fluid. And going to reiterate this from previous videos, but EGE doesn't recognize capital and lowercase letters. So even though we specified array X element 1 with lowercase and here with a capital letter, EGE recognizes that as the same variable. So it won't affect our output. We want, no, I won't do calculate itself yet. So now we're going to look to see what other quality value we can find. We look at our TS. We know state 5 is also saturated vapor. I'm also just going to note real quick so we know why we had that assumption, saturated vapor. So we'll go to state 5. You can just copy and paste this. Control C. Go to state 5, Control V. Now we need to make sure, if you're doing copy and paste to be faster, you have to make sure that you just change all these 1 values to 5, or else your output for the whole worksheet problem is going to be wrong. So just make sure, just change everything to 5. Okay, so now we solved all of state 1, all of state 5. We know that state 3, once it leaves the working fluid leaves the condenser, it's a saturated liquid. So we can go to state 3, and we know quality at state 3 equals 0 then, because it's a sat liquid. Then we can copy and paste this again. And remember, you just really important that you need to change the elements in these arrays, or else your output will be wrong. Okay. Now we also know at state 7, this also leaves the condenser, so it's also a saturated liquid in an ideal cycle. So we can just, again, copy and paste this for state 3 because it's going to have a quality of 0 since it's a saturated liquid. Make sure you change the number in your array. Now we're going to have to think of a different thermophysical property to complete states 2, 4, 6, and 8 because they don't have a quality of 0 or 1. So if we look, what's connecting these two vapor compression cycles is this heat exchanger. So we can do an energy balance for the heat exchanger. I will write this under state 8. I'll put a new comment just for a new section. Do heat exchanger energy balance. And we know that the heat into the system is m dot b times, it would be the heat into minus the heat out of the system, so the heat into the system would be H2 minus H3. So that's Q dot into the system. And we don't have H2, we found H3, we don't know M dot B, but we see here that it's a given. This is the bottom cycle, this is the top cycle. They're going to have different mass flow rates, but M dot B is known. So we'll put M dot B equals 0.05 kilograms per second. Whereas also heat into 5. So I'm not going to label this Q dot N. Label this Q dot B. So now, for the heat exchange, we'll do the upper cycle, which we'll denote as A. So we'll do Q dot A equals M dot A times H5 minus H8. And we need a value to find M dot A. We also don't know H8, but we do know H5. So we need an equation to solve for M dot A. I mean, we obviously don't know what the heat values are, but if we use the first law of thermodynamics, we know that conservation of energy, Q dot B equals Q dot A. And this is because of the first law of thermodynamics. So now we need an equation to find M dot A. So we need to do a ratio of mass flow rates. We can say, have a new variable y to represent the ratio. We can say M dot B over M dot A. Cycle B over cycle A. So this previous energy balances, we're going to adjust these equations we just typed and coded to input this, because we have too many unknown variables in this equation. We don't know H5, we don't know M dot A, we don't know H2, so we have 3 unknowns. And then again, Q dot B is Q dot A, so we can take those out. But I'm going to adjust this first law equation . Going to be y times H2 minus H3 equals H5 minus H6. Yeah. And we're changing H5 minus H8 to H5 minus H6 because it seems like a typo. Okay, so I just had a typo in my notes, so this is still H8. So if you see here, we had the same equation, except we just divided by m dot a for this first law of thermo. So we have only one unknown, which is this y value. So, in a way, I can delete these because these are just redundant. I'll title this as okay. Now let's see. So we don't know H2 yet. We do know H3. We know H5. So we still have too many unknowns because we don't know H8 and we don't know, what was it, H2. So we have two unknowns and only one equation to solve. So we'll have to leave this to the side for now. But we can still look at our TS diagram and find more common property values. We see here that the entropy at state 1 equals the entropy at state 2 because it's an ideal cycle. So we can go here and we know S2 equals S1, and we found S1 here when we called our real thermal props function. So here I'm not going to copy and paste this. You could, but just so you don't make this mistake. Here are the two independent variables of quality and pressure. Here are two independent states, or two independent property values, are pressure and entropy. So we want to make sure we have that denoted. Function, real fluids, R134A, real thermal props. Independent properties are pressure and specific entropy. We're going to paste. And this is state 2. So now we're one step closer because now we know H2. The only unknown we have for this is H8 and m dot a. But with these three equations, we could find both. So now that's good. But we're just going to continue with these constant entropies. So we're going to find more. And we also see at state 5 and state 6 is constant entropy. You can also write a comment for the reason, and that's because it's in isentropic compressor assumption. So we know state 5, we don't know state 6, so we know. We can also just copy and paste this now that we have constant entropy. Make sure you change your array values. So entropy at state 6 equals entropy at state 5. Change all this to state 6. Okay. Now we see we have thermophysical property values at every state except for state 4 and state 8. Those are not isentropic, and we had the constant pressure already, but we don't know the quality because it's a saturated liquid vapor mixture. Again, we can find now, I believe, or actually, don't look at the TS diagram now. If we look just at the actual flow diagram, we see from state 7 to 8, there's an expansion valve. So we know there's constant enthalpy. So H8 equals H7. We'll do options, function info, thermophysical properties, real fluids, R134A, real thermal props. Now we have pressure and specific enthalpy. Paste. And we need to make sure we include the 8 value. Okay, now all we need is state 4, and we see state 4 is the output of an expansion valve, so enthalpy at state 3 equals state 4. Going to copy and paste this. And then just remember it's important to get a correct output to just change the numbers of the array. So state 4 equals state 3. Ah. State 4. So we solved all the thermophysical property values at every state without needing to use first law of thermodynamics for the heat exchanger. And without the mass flow rates known. So we were able to solve all the pressure, temperature, enthalpy, and entropy at every state. So what you could do after this is know how to solve for power. So we can do energy values. And we know for a heat exchanger, power is the work output of the system minus the work done by the system minus the work done to the system. So we are going to do work into the system. This is specific work into the system is H6 minus H5. It's the work into the system with the high pressure compressor, and then we're going to add it with the low work into the system due to the low pressure compressor. So this is going to be H2 minus H1. Workout, specific workout is going to be six to 7 and 2 to 3, I believe. Okay, so instead of denoting this for energy values, we'll do them individually and we'll include mass flow rates. So we'll have so this is the compressor power of the lowest compressor, and that one has the bottom cycle mass flow rate, which is the given 0.05 kilograms per second. So we're going to have m dot b times, then it's H2 minus H1. Then the power of the high pressure condenser, or compressor, sorry, compressor, not condenser. This is W dot C high. This is going to be M dot A, which should be outputted using these three equations that we have, and then our known energy values that we solved. Because just the process, so we know M dot B, using this first law of thermodynamics equation, we have every known value here except for Y. So then we'll go into this ratio of mass flow rate, so we know Y, we know B, and then we'll find M dot A. So that's a known now. And now it's H6 minus H5. Okay. Then we're going to find, so I'll just denote this as compressor power. And this is refrigeration capacity. This will be Q dot in low. This is of the bottom cycle. So it's going to be H1 minus H4. Oh well. M dot B times H1 minus H4. Then we have Q dot in high equals M dot A times here's the evaporator, so it's going to be H5 minus H8. So that's individually. So you know the total compressor power into system, I'll just denote as Q dot C is going to equal Q dot low plus Q dot high. And we know the total refrigeration capacity of the system is Q dot low plus Q dot high. So then we can find the coefficient of performance of the system. So we'll do COP equals Q dot in divided by W dot C. So now we should have been able to solve everything. Just make this bigger. And when we calculate solve, we'll see if there's any errors in the code. Do not believe there was. Okay, so here's our array table. Where did it go? Do calculate solve again. Okay, here we go. So our ratio to mass flow rates was 0.7792. See, when we did that mass flow rate ratio, we have our known M dot B. Our M dot A was determined to be 0.06417 kilograms per second. Our heat into the high system is 10.04 watts. Q dot in low is 9.2 watts. Total is 19.24. We have our work done by the high compressor, or sorry, this is power, not work. Power done by the high compressor, power done by the low compressor, or total compressor power, and then we have our COP is 9.354 as our ratio here. Then we can look at our array tables for thermophysical property values, and we have all the states defined. They look good. And then if you want, you can right click this main title. You can hit save. We can save as an Excel file. Okay, so I'll save this as Cascade. Go into my folders. Now we have an Excel file. And I only specified in my code the units for pascals, but I could have also inputted them for the other arrays. So if you want to do something in Excel, you have this. Now we can try to replicate the TS diagram. If we look at the sheet, see that we have, it's going to go from 1 to 2, 2 to 3, 3 to 4. But then it's going to go from 4 to 5 here, which isn't correct. I'm not sure how we would do this. Before in the previous video, we had it go smoothly that way, where it's a closed system that connected. But here, there's one closed system, and then there would be another closed system. So that's something you could figure out on your own if you wanted to create a TS diagram. But we found all the thermophysical property values, mass flow rate of the top cycle. We found power into the system, power out of the system, and we found the coefficient of performance.